right, welcome everyone to Proofs Day. First, a quick announcement. Friday evening, we will have a Crypto Beer night. This is not Simon's event. This is just something some of us, Sanjam, myself, Putek, and others like to organize every so often. And this version will be this Friday at 5 p.m. just across the street at Free House. Everyone is invited. Okay, so now for the agenda. So today we are talking about proofs, and we have three speakers. There were two on the schedule, but we decided to do a switcheroo. So first we will have Alex and then Yael talk about proofs on the theory side. And then in the afternoon, we will have Justin talk about more applied side of proofs. So Alex, please.
Hey, everyone. And first of all, thanks so much to the organizers for putting together the workshop and the whole rest of the summer program. I just got here last night, but I'm really looking forward to the summer. And also, I'll apologize in advance. You were expecting Yael, but you were stuck with me. But that's okay. But in any case, I'll give the first half of this theory intro, and Yael will dive deeper into some of the later topics in the next talk. All right. So, okay. Final disclaimer is that when I was preparing this talk, what I kept thinking was that I would like to have the entire day to give the talk instead of 1 hour, because this field is so cool, and I would like to talk for many, many hours on why this area is so fun to work in and all the kinds of open problems. And of course, we're pressed for time. We have an hour, but I'll try and convey some of the.
That's a good idea to have a series of talks during the semester.
Yeah.
Yes, that's a good idea. Yeah. Hopefully, it's not just me giving the entire series of talks. All right, so let's start. So the first thing to remember about proofs in the context of computer science is that I consider it to be one of I don't know why I'm saying our, it was in the past, but one of the field's greatest accomplishments in abstractions and like problem definition. Because up until quite recently, like history-wise, people didn't talk about proofs in the way that we're talking about them in this workshop or in this program. So, you know, when I try to introduce proofs to people that haven't seen them before, I say, well, here are my two examples of proofs. First example of proof is an axiomatic derivation, right? This is the thing that you're taught in school about. This is a math proof. You have axioms, you have a formal conclusion you want to derive, and you have some derivation rules. But you know, even before computer science, this isn't the only thing that was a proof. In fact, the much more common form of proof was actually something like a seminar talk. This is for those of you who haven't seen this picture before, this is a shot of Andrew Wiles presenting his first proof of Fermat's last theorem, which for additional intrigue was actually incorrect and had to be fixed. But this shot appeared in this proof was so famous that it appeared in the New York Times. So yeah, this is when people talk about proofs, this is what a lot of people would have in mind. Okay, and of course this is not a formal derivation, but simply a talk that convinced people, actually incorrectly at the time, but after some work actually convinced people that one could produce an axiomatic derivation if one were really forced to. All right, so this is what, you know, of course, there are many other notions of proof that I haven't even touched upon. Philosophy has its own things to say on this topic. But so what are we doing here? We're not doing, I mean, we are doing this, but the proofs that we're studying are not this. Yes. Oh God, I actually have no idea. Yeah.
The square is at all time. Square is all time periods, and diamonds is eventually.
Ah, wow. Okay, thanks.
It's just a picture. Okay? No, but it's temporal logic. It's called temporal.
It means you know the right font and stuff.
All right. Anyway, so So what are we doing here? So theoretical computer science and cryptography in particular had some very interesting insights that turned this into an entire field of study. And so the first insight even kind of predates cryptography, which is that you can think of producing a proof as a kind of computation. So I'm not sure actually who the right person is to, or the right place to cite this idea, but it at least appears in an early work of Cook on proof complexity. Maybe you need to go even further back. One could argue that even a definition of a complexity class like NP is already doing this, but since NP was originally about non-deterministic Turing machines, I'm not sure if this is the right viewpoint to have. But at least when you're talking, like as soon as you're talking about proof complexity, you've certainly done this, and this is not an obvious thing to do, I think. If you just start with the previous slide. Okay, but now we get really. I guess I have a particular thing in mind to cite, but maybe I cited the wrong thing. All right, so second insights, which is an even bigger departure from what we just talked about, is that the natural way to formulate the proof as a computation is what I've already written up here, which is you have one entity, a prover, that writes down a proof, and one entity, a verifier, that checks the proof. But the natural thing to do would be to say, well, write down the proof and then check the proof. But what you could do instead is consider a process for generating and verifying proofs that allows interaction between these two proving and verifying parties. And furthermore, allowing these checks even to be randomized. And finally, the third insight that really so of course, this insight alone is already going to give you a ton of interesting theory, but it's still arguable whether this is cryptography. But you definitely get cryptography when you have this third insight, which is that instead of talking about, for example, a perfectly sound proof system where it's impossible to prove something that is false, instead, think about the parties in your proof system as being potentially adversarial, and furthermore imposing the constraints that the adversaries in the proof system are computationally bounded. So at this point, now it's really, really cryptographic.
Can I ask a question? The idea of interaction makes sense only when you assume not all parties are equal, right? Otherwise, why would you need interaction? Like one party has the witness, or one party is computationally unbounded, or something.
Yes, certainly. So yeah, and I agree. It hasn't come into play here, but yeah, I'll give the formal definition on the next slide.
That's the point of a proof, that one has a proof to give to the verifier. Otherwise,
no, I think it's not yes, that's what we ended up with. But I agree that it hasn't been argued.
Somehow randomization seems to me helpful, even if everybody's identical in everything. I don't know. Whereas interaction is only helpful if somebody knows more. But you're right. Yeah, and yeah. If I want to prove I have the proof and you don't, that makes sense. Anyway, yeah.
No, it's true. This is like back solving the model that we ended up working with, but it's not obvious this is the only thing that you do. All right, but nevertheless, this framework for talking about proofs, of course, probably everybody knows, very famously, appeared in this work of Goldwasser, Macaulay, and Rakoff that introduced this model. If you only care about this second idea, it also appeared in a work of Babai on defining Arthur Merlin proof systems. Okay, so more formally, here's the model. We have two parties, a prover and a verifier, and for the entirety of today, we'll be talking about proofs, at least for the first two talks, and most likely also in all of Justin's talks. We're going to be talking about proof systems for NP languages. So that is, you have an NP language L, and the prover and verifier have shared an instance X, which allegedly belongs to this NP language. And the prover's goal is to convince the verifier that indeed X belongs to this NP language, which means that there exists an NP witness for that statement. And so the prover and verifier will execute some interactive algorithm, and at the end, the verifier has to output a bit indicating whether or not they believe the prover. And so in this model, we'll always have the verifier running in polynomial time, which somewhat addresses Tal's question from before. And the prover, on the other hand, you can either model as being computationally unbounded, because finding an NP witness, for example, is in general hard. You can't expect them to be able to run this protocol where everybody runs in polynomial time and nobody has the NP witness. Or alternatively, and this will actually happen for basically everything that we discuss also, the prover is going to be modeled as actually running in polynomial time, but having been provided an NP witness so that it is reasonable to do this. And yeah, so these are called efficient prover protocols. And if you ever want to run a proof system in practice, then you're going to want an efficient prover. Okay, and so the basic properties that you ask a proof system, an interactive proof system, to satisfy are completeness, namely if the statement is true, and the prover and verifier both run their algorithms properly. Then the verifier should accept with probability 1. You could relax it to some large probability instead, but we'll just stick with probability 1. And the soundness property can be phrased in one of two ways. Like they're called statistical and computational soundness. But they both say that when the statement is actually false, you want some guarantee. You want it to be hard or impossible to prove false statements. So the property says that either for any prover strategy P star, the verifier should not accept with high probability, so here accept with probability at most epsilon. This is called the soundness error of the protocol. And so this first definition is called statistical or information theoretic soundness because the prover is allowed to be unbounded. You can also just require something weaker called computational soundness, where you require the same thing, but only for polynomial time adversarial prover strategies. Okay, so these are the basic parameters of the model. And so yeah, it is a form of computation that describes the process of an untrusted prover proving something to a computationally bounded verifier. Okay, so I've already hinted at it because if you make any computational assumption, then maybe you're doing cryptography already. But still, especially if you're not thinking about computational soundness, it's really not clear what this model a priori actually has to do with crypto. And indeed, you can define it. It's perfectly reasonable to define this model without even thinking about cryptography. But still, there is an entire field of cryptography that is sprung out of this, and there are two key reasons why, or two key features of proof systems that we end up wanting to aim for that both seem to require the use of cryptography. And so what are these two things that we want out of proof systems? And of course, this is in very broad strokes. There are more things that you want out of proof systems that I'm not talking about, but here are two very important ones. So the first thing is you want some form of secrecy for the honest prover. So the honest prover has some NP witness, and they can use it to prove that a statement X is true to some verifier. But the problem here that we're trying to solve is that maybe this NP witness W is a secret or contains some secret information that you do not want to leak to other people. And indeed, you may not even trust the verifier to run the protocol properly. One thing you could do is you could design a protocol so that if the verifier, let's call it a public coin protocol, if the verifier just sends random coins as their messages. So a lot of protocols that we consider will have this property. And maybe you could design a protocol where the verifier is supposed to send just truly random coins. And if they send truly random coins, they won't learn anything about your witness. Great. But maybe if they don't do that, and they send some specific weird messages instead, maybe they can learn something about your witness. That would also be bad. So we want to protect information about a witness from a verifier that either actually follows the protocol or even deviates from the protocol. Okay, so that's property number one that we care about. And so there is a, like, you know, already back in the 80s, we had a security definition, which is so strong that it certainly like should like stop you from worrying about this, basically. So the property is called zero knowledge, and I'm not going to spend too much time on this definition because I assume that most of you or all of you have seen this already. But a proof system is zero knowledge if you can efficiently simulate the view of a polynomial time verifier, in the execution of a protocol with the honest prover. So there are two things that you want to say are indistinguishable. There's what this verifier V star would see if they executed the protocol with the honest prover. This is what this view thing is called, and it's just their random, like you can think of it as just their random coins and all the messages that the prover sends. And what this definition requires is that this view is computationally indistinguishable from the output of some efficient simulator run only on the NP statement X, and in particular, the simulator is not given the NP witness, which is what the prover uses to actually generate the prover messages. So if you can simulate your entire view without the witness, then this is pretty strong evidence that you are not learning anything meaningful about the NP witness. Yeah, so this is one of if not the first example of what is now known as the simulation paradigm in cryptography, which for example is used to great effect when studying multi-party computation, which you'll learn about, I think, tomorrow. Yeah. Okay, so this is zero knowledge. And so to first order, when you want secrecy for the honest prover, what you're looking for is called a zero knowledge proof. It's a proof system that satisfies the zero knowledge definition that we just discussed. So the second thing that you want is to save the verifier work, right? This is actually much more modern, I would say, desirable feature. Not that we didn't think about it in the past, but it's become much more prominent recently because of applications of practice. And so what you end up asking for here is you could say, well, in a trivial proof system for an NP language, the prover can just send the witness and the verifier can just check. The problem here that we're trying to solve is not that we want to hide the witness, but that perhaps, depending on your choice of NP language and your choice of input length, the work that it requires to verify just that an NP witness is valid for a statement may be very large, and the verifier may not have enough computational power to do this. And so one way to state this kind of requirement is that we can say that we would like the time that the verifier has to run to at least be sublinear and possibly very small, like even polylogarithmic, in the size of the NP witness, which certainly rules out this trivial protocol of sending the witness. And indeed, although we have not actually formalized this, seems to require the use of cryptography. Seems to require the use of cryptography and seems to only be possible in a setting where soundness is computational, where you assume that the adversarial prover is computationally bound.
That's the third place where cryptography comes in, soundness. This seems to me like the most.
Yeah, so I would say, yeah, I guess, but the way I would phrase it is that this verifier work requirement imposes this constraint on soundness being computational, and that's why there's cryptography. But yes.
Without this requirement, if you have an argument system.
Yes, certainly. But
soundness.
if you didn't have this requirement, maybe we could have just been working with statistically sound proof systems in the first place. But maybe not. There are other reasons.
I understand your point now. Yeah.
But yeah, there are certainly other ways of arriving at this computational soundness without going to it.
So, I mean, PCP, the verification would be sublinear and no crypto.
Yes, but it's sublinear in a computational model, which we're not working with here. So in particular, I will impose that the verifier has to at least read the entire message that the prover sends.
Maybe communication and verification.
Yeah.
Yes, that is yes. Okay, and indeed, that's what we'll do. So so a proof system is called succinct exactly if the proof length is short, polynomial in whatever security parameter you're using, and polylogarithmic in the instance and witness length. And you also require the verification time to be short, where you have to worry a bit about this, whether or not reading the prover message counts as verification time. So I have the parameters set up so that it's basically quasi-linear in the amount of time that it takes to read the input. Sorry, not just the prover messages, but the input. So if you think of the security parameter lambda as being very small, then it's kind of quasi-linear. So yeah, so when talking about succinct proof systems, you have your input length and you have a security parameter, and you usually think about the security parameter as being very small compared to the input length. Certainly very small compared to the witness length. Okay, and so when you have this kind of protocol, a protocol satisfying these succinctness requirements, we say that we have a succinct argument system. And so if you're thinking about what crypto theorists are thinking about proof systems, of course there are a ton of things that we're thinking about, but to very first order, two things that we care a lot about are building zero knowledge proofs and building succinct arguments. And it's actually really amazing how much these, I would say innocent looking definitions, innocent looking primitives, how influential they turned out to be in the entire cryptographic landscape. So they're a really important foundational building block for all sorts of things that you do in crypto. Just to quickly name 3 examples, at least if you squint at it properly, you can think of proof systems as underlying at least one of the main ways we have of building digital signature schemes, which of course are used all the time on the internet. On the theoretical side, they are one of the key tools used to obtain protocols for general purpose secure computation. In particular, what's the point of a proof system here? The point of the proof system in such a protocol is for a party in an MPC to prove that they are behaving honestly. So it's a way to go from MPC protocols that are secure against semi-honest adversaries to a protocol which is secure against fully malicious adversaries. And then finally, more recently, especially some of these newer blockchain and cryptocurrency protocols have started to use even fancier proof systems like succinct arguments to sort of expand their functionality. And so Justin will be talking a lot more about what of proof systems you want for these blockchain protocols in the afternoon talks. Okay, but already here are 3 really big application domains where proof systems are really, really crucial. Okay, and finally, just to, I guess, finish my pitch on why proof systems are really fun, even if you don't have I guess, quote unquote, real world applications in mind, it turns out that thinking about this model that we described just teaches us a lot about the nature of computation as a whole. So, and again, I would need an entire course to describe this, but at least here are 3 of my favorite examples of instances where this has occurred. Of course, proof systems were interactive proof systems, etc., were extremely influential in complexity theory for their role in leading to this IP equals P space theorem, characterizing polynomial space computation in terms of interactive proofs, and the PCP theorem, which says that there is an information theoretic proof system for verifying NP computations reading a very small number of bits of the proof. Then more recently, And so these are the next two are applications of non-interactive proof systems, which we haven't gotten to yet. But nevertheless, in game theory, it turns out that you can understand the computational complexity or computational hardness of computing Nash equilibria, which a priori have absolutely nothing to do with proof systems, in terms of the hardness of breaking the soundness of certain kinds of proof systems. This was first observed by an early work of Valiance, and in more recent years, we've been able to use these and related ideas to show that computing Nash equilibria is hard under cryptographic assumptions. And finally, there's also a lot of interesting connections between proof systems and quantum computation, where one go-to example here is that you can imagine sort of hybrid quantum classical computational model where the prover has quantum capabilities, this more powerful prover, and while the verifier remains classical. You can ask, can the prover demonstrate quantum capabilities? That's called a proof of quantumness. And you can ask, can a verifier just in general delegate an arbitrary quantum computation to the prover and trust the result? And so based on works like starting from Mahadev and many works since then, we've learned a lot about quantum computers by thinking about proof systems. Yes.
Succinct or not?
Well, the original protocol was not, but now we know how to do it succinctly.
You also need to define kind of system.
Yes, but the definition is basically the same. All right, so that's why proof systems, or that's a very short summary of some of the reasons why proof systems are so cool to think about. So now let's actually get to business and say, okay, can we build these things? So the two classical results here are that you can, and these are about interactive proofs, are that one, you can build zero-knowledge proofs for every NP language. This is due to Goldreich, Macaulay, and Vigderson. And the second big theorem is that you can also build succinct argument systems for every NP language. So let me, so I guess to go a little more slowly, the so these are crypto results. We have to make computational assumptions. The computational assumption you have to make to get zero-knowledge proofs is the minimal assumption that one-way functions exist, which is great. And at least in the classical result, in order to get succinct arguments for NP, you assume something slightly stronger, but still very standard and reasonable, namely the existence of collision-resistant hash functions. Hash functions or distributions over hash functions where it is hard to find, given a description of the hash function, a pair of inputs that collide under the hash. Okay, and as we've been discussing already, like when you want to build a succinct argument system, basically the best you can hope for is computational soundness, and that's true for this result. This result is due to Killian and Macaulay. If you like, you can also make these things zero-knowledge. And indeed, nowadays when people talk about succinct arguments in practice, they always assume that they're zero-knowledge, and sometimes call them actually zero-knowledge proofs. Yes.
Do you believe that we need collision resistance here rather than just one more?
No, this is one of the open problems, and
Can you repeat the question? I didn't hear.
Is there a reason we should believe that collision resistance is necessary rather than homogeneous here?
yes, so I'll try and get to open problems very quickly where I'll mention this. Okay, so I'm assuming that many of you have seen proofs of these theorems before, and I'm not going to cover them in full detail, but let me give a brief word on it anyway, and maybe offer a perspective that slightly fewer of you have seen before, which is that these theorems, if you squint a little bit, they're basically the same. The proofs of these theorems are also basically the same. If you know the right language to use, of course not a priori, but like with a modern view, you can think of these proofs as basically being the same. And so this is a perspective that I've seen advocated for, especially by Yuval Shai. And I think you probably find many talks by him on this, which is that you can think of the process of building these cryptographic proof systems as being composed of two steps. One is that you construct some sort of interesting information theoretic proof system, And the right object for these two theorems turns out to be something called a zero-knowledge probabilistically checkable proof. You don't have to worry too much about what exactly that means, but there's some information theoretic proof system. And then you apply a cryptographic compiler to turn this information theoretic proof system into the cryptographic protocol. And the cryptographic compiler that is used for both of these two theorems is something called commit and open.
It's called what?
Sorry, what?
Is it called what? Oh,
It's called commit and open. Yes. Yes. So very briefly, like what's going on here? So like I said, the information theoretic proof system that you use for these two results is called a PCP. And in a probabilistically checkable proof is a different kind of proof system. Like it has a different computational model for verification. So in a PCP, you start with a witness. To generate the proof, you write down some encoding of this witness into what's called a PCP string pi. So it consists of many bits. In general, you can think of this as being like many blocks, which is why it's written like this. But we can just think of each piece as being a bit. And the verification procedure in a PCP is two steps. One is you sample from some distribution a query set S, which is supposed to be a small set of locations of the proof. The verifier reads this small number of locations, and then performs some sort of check on the results or on the values on the bits of the proof written in those locations. And so we say that the PCP is locality L if you only read L bits and make a decision based on what's written in these L locations. So when you normally learn about PCPs, this is it. It's just written, and like what you want is completeness and soundness, just like before. But you can also talk about what it means for a probabilistically checkable proof to be zero knowledge, which has a few definitions. But for our purposes, the way you can think of it is like what's going on here is that you should think of the verifier as only being able to see what is written in these L locations. And so we want this proof. Of course, this entire proof is not like, if a verifier sees this entire proof, this is not zero knowledge in any reasonable sense. But if you model the verifier as only knowing the bits written in these L locations, we can say that this kind of proof is zero knowledge if for any valid query set S, it is possible to simulate what the verifier sees in these L bits. You can simulate the distribution over L bits, in a way that's indistinguishable from taking a valid witness, encoding it, and then just reading the L bits. So in particular, to have this kind of property, of course, this encoding procedure is going to have to be randomized, but that's fine. We can allow for that if we want. Yes?
So which of those two applications is captured?
Both.
Both separately or both at the same time?
Well, that kind of depends on your point of view, but I would say effectively at the same, well, both separately and at the same time. You can, everything. Yes, the answer is yes.
Is the CKPCP the reason why succinct proofs can be made zero knowledge? There's some other.
It's certainly one reason, and I think if you look at, okay, that's not how Killian did it, if I recall properly, but it's certainly one way you can do it, and most likely in practice, it would be better to work directly with a zero knowledge PCP, because the other way of doing it, you can generically make a succinct proof zero knowledge by some sort of composition theorem. There are in fact multiple ways of doing composition theorems, but this is certainly not efficient in practice. This is a good way to have zero knowledge succinct arguments.
Like even if you do some kind of like MPC in the head approach for making zero knowledge, is it clear that that's less good than starting with a zero knowledge?
No, I mean, yeah. Again, this is very philosophical, but you should definitely think of MPC in the head as writing down a zero knowledge PCP. Like that's what it is. If you think about the collection of all of the views in the MPC, that's the zero knowledge PCP.
But, maybe I'm wrong, but I remember reading in various papers on this type of applications that they say, oh, we focus on succinctness because the zero knowledge can be added at the end as an after step. And these are typically papers that care about efficiency. You're saying that adding zero knowledge at the end is not an efficient way to achieve it.
Yeah, because you're going to, when you do that, you're going to, in particular, be making non-black box use of cryptography. You're going to be running a proof system on a cryptographic, like a computation which involves cryptography. So if you're really trying to optimize efficiency,
Daniele, because I think that actually you can think of MPC in the head as a generic approach for doing that, right? So you take any PCP you want, and then you make it zero knowledge using MPC in the head.
yes. So this is not, I guess, most likely the way you're thinking about it will not involve this non-black box use of cryptography, right? You're doing an information theoretic. You're doing an information theoretic MPC on top of your piece, like your
PCP,
yeah. You're doing PCP verification with an information theoretic MPC, right? It's probably.
But it's still a generic approach. You can, if you take that view, you can just focus on building normal PCPs without zero knowledge.
I think Alex was talking about composing succinct proofs with zero knowledge.
Yeah.
One way or the other. That's
But it's like you can do it either black box composition with zero knowledge or non-black box. If you do black,
Yes, but I guess what you're saying here is that in the context of PCPs, you can think of zero knowledge as something that you can add on generically at the end, which is different from the statements that you can add zero knowledge on at the end of succinct arguments. These are both things that people say, and yeah, they have different costs.
This
That's
is not like what's gonna,
finally
this is not practical even without the zero knowledge.
Yes,
For practice work, there's other
Yes.
parts that Justin will talk about.
yes, for sure. Okay. Nevertheless, like you can think of this as being a good information theoretic building block for building proof systems, albeit it's not the most efficient way. This is
Not practical about it.
the generating a PCP is expensive. That's what's not practical, basically. Is it? Yeah, what's not practical is the runtime of the prover. Okay, and okay, so but indeed you can think about two different zero knowledge PCPs which capture the two classical theorems. So one is for example, a PCP for the graph 3 coloring problem where you start with a 3 coloring and your quote unquote encoding of the 3 coloring is just another 3 coloring where you've randomized the values of your colors. So it's not a very redundant encoding. It has the same length as the original witness, but you have done something to make it zero knowledge. By randomizing the colors, you make it zero knowledge because if you think about the process of verifying a 3 coloring proof, like it suffices to just read 2 bits, the colors, or not 2 bits, but 2 trits, the corresponding to 2 colors for a single edge of the graph, and checking that they're not equal. So if you randomize the colors, then for a verifier that can only read these 2 trits, they won't learn anything, because all they'll see is a random pair of unequal colors. On the other hand, this is not how you normally think of PCPs, because originally the idea behind studying PCPs was to get a good trade-off between the locality and the soundness error. You wanted to have good soundness while not having to read a very large number of bits. Whereas here you read 2 bits, but you have terrible soundness error. It's just barely non-trivial. Yes, that is yes, for sure. So yeah, the other thing you can do is invoke the PCP theorem. So one example which sort of comes up in more theoretical works on succinct arguments is the BFLS PCP, but you can use more modern PCPs as well. And here you can still have very small locality, which will turn out to matter in the cryptographic application, but get much better soundness error. All right, and then the way that you get the classical results, the classical proof systems, is by taking your favorite zero knowledge PCP, for example, one of the 2 that we just mentioned, and then applying some sort of cryptographic compiler. The cryptographic compiler here is called commit and open, and what happens? The verifier sends a key to some commitment scheme. The prover generates whatever PCP string, like a PCP string according to the information theoretic proof system, and sends a commitment to it. The verifier then selects the query set for the PCP and sends it to the prover. And then the prover opens not the entire PCP string, but just the locations corresponding to the subset S that the verifier wanted to read. And then what the verifier has to do is two things: verify that these openings are valid, and perform whatever PCP check that they were supposed to do. And yeah, this is an extremely influential paradigm, which is used all over the place, and in particular captures both of these classical results. To get zero knowledge for NP, basically now all it comes down to is you get the two results by specifying what the PCP is and what the commitment scheme is. So to get zero knowledge, you need a commitment scheme which computationally hides the bits that you're committing to, and you could imagine applying this commitment scheme bitwise. And it's known how to do this assuming just one-way functions. And you can use this randomizing three-coloring PCP, and you get zero knowledge proof system, albeit with poor soundness error, that then if you wanted to have good soundness, you would have to repeat sequentially, it turns out, several times to reduce the error. To get a succinct argument for NP, we just have we make two different choices. What it turns out you need here is a commitment with succinct local openings. You need to be able to send a short commitment and also be able to reveal individual bits of your long message with short certificates. This is also sometimes called a vector commitment, because you're thinking of yourself as committing to a long vector, but wanting to open to individual entries of the vector. And then it suffices to use any PCP with good soundness locality trade-off, and then this commit and open protocol that we described will give you a good succinct arguments. And moreover, with a very small amount of additional thinking / work, you can argue that this kind of proof system can also be zero knowledge. All right, excellent. So why aren't we done? So far we've had maybe a modern perspective, but on results up until 1992. So what do we do now? What have we been doing since 1992? So we've been doing a lot. So here's the situation. Even just thinking about interactive proofs for a moment. We have these two big existential results saying you can, if you want zero knowledge, if you want a succinct argument, it can be done. But here's there are a ton of things that you could try to optimize and simultaneously optimize about cryptographic proof systems, and I've listed a bunch here. You would like to minimize round complexity, how many rounds of communication suffice for proof systems. You would like to minimize communication complexity, which succinct arguments sort of already do, but you can ask this in other contexts. For example, what if you want to minimize communication complexity but also have information theoretic soundness? Then there's an entire different thing you have to do. We'd like to optimize the verifier running time. Again, that's one thing that happens in succinct arguments. But the things that we haven't discussed so far are that you might want to minimize the time or even space complexity of the honest prover. This turns out to be very important when designing a practical protocol. And there are many ways of thinking about this problem of quote unquote doubly efficient interactive proofs, and there's an entire day's worth of things to talk about on this. You can also talk about achieving qualitatively different kinds of security and what sort of trade-offs this creates. That is, is your security computational or statistical? Are you really achieving zero knowledge, or maybe you're just achieving some some relaxation of zero knowledge that hopefully still suffices for you? So there are a whole host of security definitions that are, for example, relaxations of zero knowledge. There's also this notion of proof of knowledge, which we haven't talked about at all. You also might like to optimize for the concrete security of the protocol. This is something that Justin will be talking about. And you also may want to optimize or to minimize the computational hardness assumptions that you're making in your proof of security. So there's, several decades of research compressed into one slide here. So with this in mind, let me mention a few open problems in the area that I think are nice. So one is the round complexity of zero-knowledge arguments. So right now we have a work of Vitansky, Kalai, and Peneth, who construct 3-message zero-knowledge arguments for NP, but under a non-standard assumption. It's a reasonable-looking assumption, but it's called keyless multi-collision resistance, but not something that we understand terribly well. And this is basically all that we know. So the conjecture is that, or the suggestion here is that 3-message zero-knowledge should be possible, and we have some justification for this. But it'd be wonderful if we could show this is possible under more standard cryptographic assumptions.
If you think of Fiat-Shamir as a non-standard assumption,
Yeah, but you shouldn't think of that as being okay. Well,
it is more standard than Fiat-Shamir.
No, I would say that Fiat-Shamir does not give you a zero-knowledge interactive proof system. That at best you can think of that as being if you want something in the plain model, at best it's a 2-message proof system, and then it's not going to be malicious verifier zero-knowledge. Yeah, so it's actually a different question. So another question, which is a little surprising to me that it's open, is understanding the minimal computational assumptions needed to build distinct arguments. So the classical result says that it suffices to have a collision-resistant hash function. There are some more recent works that relax this slightly, and they show that you can build it from this thing called multi-collision resistant hash functions where it's hard to find a rarer, a rarer string, a collection of many inputs that all hash to the same value. So this is a weaker hardness assumption. But ideally, whenever we have a simple cryptographic primitive, we hope that you can build it just from one-way functions alone. But this is completely open. And so there are a couple of interesting recent works on building succinct argument systems for restricted languages from one-way functions by Amit and Rothblum, but they're not about succinct arguments for NP. And I'd say it's quite unclear, even which direction we expect here. Maybe we'll be able to build them, maybe we'll be able to provide some evidence that this is hard, but we don't really have either of those right now.
Alex Motto and I had this paper in 2010 showing that fully black box construction are unlikely for NP based on one-way functions. If you want zero knowledge succinct.
No. Okay. This is about succinct arguments, not about zero knowledge, but
okay, just succinct. Yeah. If you add the zero knowledge, then it's unlikely to get.
If I remember correctly, the result of Toga and Guy Rothman that they rely on one-way function, but on things that you can do information theoretically if you had more rounds.
Yes. I didn't want to get into it, but I just want to say there are interesting recent protocols vaguely related to this, but they do not answer this question. It's also not known whether one-way functions are even necessary here, unlike almost every cryptographic primitive that you've ever heard of. Here we don't know the succinct arguments for NP, for example. Even if you want to make some additional complexity theoretic assumption like P not equal NP or something like that, it's not known that this implies the existence of one-way functions. I think is a somewhat embarrassing open problem, but there are actually reasons. There are somewhat good reasons why this is tricky to think about, but I'm still hopeful that there's something that you can show. Yes.
Do we have a partial result if I impose sufficient enough succinctness?
No, there's really nothing.
Okay.
Yeah. Yes.
What are the good reasons that this should be?
The reason is that if all NP languages can generically be made to have NP witnesses of polylogarithmic length, then every NP language has a succinct argument system, even an information theoretically sound one. And this is incomparable to the P versus NP problem. So the appropriate theorem statement here is a little bit complicated. You could, of course, hope for a theorem statement like a succinct argument for an NP language which does not have an information theoretically secure succinct arguments implies one-way functions or something like that. But it takes a little bit of thinking to come up with the right thing to say here.
Can you repeat the condition that implies information theoretic succinct argument?
Oh, it's pretty tautological. It's just if every NP language can generically be made to have an NP witness of polylogarithmic length. If NP is contained in NP with polylog length witnesses, then you have a succinct argument, the trivial one. Just
I understand.
yeah, exactly. Yeah. So yeah, one would certainly hope that if you make a strong enough complexity theoretic assumption, which rules this out, that you should then be able to take that plus succinct arguments for NP and get out one-way functions. But we don't know how to do that yet.
Yeah. I mean, what you said implies NP is in a quasi-polynomial time.
Yes.
Yeah, okay.
Okay. So something that we have not talked about at all so far is post-quantum security, which turns out to be very tricky to talk about for proof systems because of the way that we analyze the security of interactive protocols. In particular, something that very frequently comes up is this notion of rewinding, where you want to run an adversary several times, like from some partially completed, from some execution, from state of execution in the middle of the protocol. This turns out to be very difficult to do when your adversary is quantum. And right now, we basically have a bunch of ad hoc security proofs for protocols that we care about, but no very systematic understanding of when you can say a protocol is post-quantum secure, assuming that your cryptographic building blocks obviously are post-quantum.
So why would you call this ad hoc versus what has been done classically? So because you had like a blueprint, they could say like the one you showed.
Yes, no, that's true. You can have blueprints and you can show post-quantum security of the blueprints. That is something that people are doing. But what I would really hope for is not having to reproduce all of classical cryptography, like all of the proofs that appeared in classical cryptography to get post-quantum versions of all of the things that we got.
So you want to say some conditions on the classical constructions that will make it automatically quantum
Yes, on the proofs.
Yes.
Condition on the.
Yes.
and the constructions.
Yes. Yeah, you can think of the proof as part of the construction. Yes, that's what I would like. Okay, and then finally, bearing in mind that the way we got here is by having very interesting abstraction and a non-obvious abstraction that proof systems were. It seems worth spending more time trying to come up with interesting kinds of interactive proofs in different computational models that aren't captured by this NP language framework that we started with. Of course, one thing that has been happening very recently by Shafi, Guy Rothblum, and others is trying to apply the sort of conceptual framework of proof systems to problems in machine learning. And so maybe we'll hear a bit about this on Friday. But this is just one example. Okay, so originally, this was supposed to be the first half of the talk, which does not seem reasonable right now. When do you want me to stop? I'll just talk a little bit about removing interaction. I also don't remember when we started. When do you want me to stop?
Actually, I think it's supposed to be the break time now.
Yeah, but we started late. You can't do that to me. Yeah, sure. So, okay. So, yeah, sure. What's up?
You said you wanted to not have to redo the classical proofs to show post-quantum security. Why do you expect that to even be true? Like, why would you expect existing constructions to not need modification?
Because even if I challenge you to come up with protocols which are classically secure but quantum insecure, we only have extremely contrived counterexamples. Basically, the only way we know how to do it is to insert a proof of quantumness to create a bad-looking protocol. But those are basically the only examples we have where something bad happens. there are some caveats here, but to first order, this is true. Okay, so yeah, of course, the talk was originally titled "To Interact or Not to Interact." So based on what we have discussed so far, it's maybe not obvious that that's a question that you're even allowed to ask. Like why should you have the option not to interact? But an absolutely crazy thing, which underlies, in particular, all of these recent practical developments that Justin will talk about, is that we actually do have a choice not to interact, that despite how amazing this interactive proofs model seems to be, how much it seems to allow us to do that you couldn't do like before coming up with the model. It turns out that there are ways of doing this also without interaction, as long as you're still making computational assumptions on the parties. It turns out that this third bullet point that we in the model, allowing the adversaries to be computationally bounded, suffices to get a lot of the amazing applications that the interaction turned out to be not so necessary. So, like, okay, if you take this too literally, it's not true. So, like, truly one message, zero knowledge, and succinct arguments it's pretty easy to show that they're impossible. So the way that you handle this is by working in what's called the common reference string or common random string model. So this is a model for non-interactive proofs. So the prover sends only one message to the verifier, but they have access to shared randomness, either sampled, either uniform or sampled from some reasonable distribution. In order to run these protocols in practice, and also theoretically, it's convenient if this common randomness is public coin, so that you can because otherwise you have to wonder where this common reference string comes from. Yeah, your options are basically either run an MPC to generate it, or like if the common reference string is public coin, then maybe try to use some ad hoc sources of randomness. For example, like a hash function to generate this reference string. And then so in this model, everybody has this common reference string, and then you can talk about zero knowledge and succinct arguments in this model. And it turns out that just adding this common reference string, makes the impossibility results seem to go away, and reopens the problem of building these nice cryptographic protocols, but now without any interaction. This also has the really nice feature that it makes all these proofs publicly verifiable. So in an interactive proof, you're only proving something to one person, but in a non-interactive proof in the CRS model, you generate one proof, and anybody who has the reference string can also verify the proof, which turned out to be very nice. And so what's known here? It turns out that it's possible to build non-interactive zero-knowledge protocols for NP in this model. And we know how to do it from a whole host of computational assumptions like factoring, bilinear maps, and learning with errors. And DDH. So in terms of so basically most computational assumptions that we know imply public key cryptography, we also know how to use now to build non-interactive zero-knowledge proofs. But notably, this is a very recent development. Up until about 5 years ago, we had just a couple of constructions, but now we have a whole host of constructions.
The MQ assumption?
Hardness of solving multivariate quadratic equations. But the plus here means you need to make both. You need to assume two things. All right, so yeah, until recently, we just had a couple of constructions, but now we actually have a ton of constructions. Unfortunately, for snargs for NP, this is called snargs are succinct non-interactive arguments. We know much less, and the two main things that we know are a heuristic construction. Yes. And yeah, so one construction here to highlight is a heuristic construction that just uses a hash function. So there's a heuristic non-interactive zero-knowledge proof for NP where the common reference string is just the description of a hash function. And it's a very nice It's a very nice kind of protocol with the major theoretical caveats that we don't have a proof of security. We just have a heuristic way of analyzing. So now, if you want succinct arguments for NP in one message, these are called succinct non-interactive arguments, or SNARGs. The situation is not nearly as good. We again have a heuristic construction due to Macaulay, but that's almost all that we have. The other main construction that we have is due to Sahai and Waters, which says if you have indistinguishability obfuscation and you let your reference string be an indistinguishability obfuscation of the NP verifier for your NP computation, so like a giant obfuscated program, which also has some cryptographic operation inside it, then you can use this also to build a succinct non-interactive arguments, like in this model where you have this giant structured common reference string. So these are the two main constructions that we have. Very recently, we know something a tiny bit better than this in a work from this year with Zheng Jin, Yael Kalai, and Surya Muthiyaragan. We show how to make the reference string of this Sahai-Waters proof system public coin. So this removes like one caveat from the Sahai-Waters construction, but requires still this like IO assumption, which is super strong, and we like throw on an LWE on top of it. And so basically, like if you think about like what assumptions are known to imply SNARKs for NP, we have IO and heuristic, and it's open to do anything better than this. So like one like big open problem that I want to highlight for I guess this program and beyond that is to understand how to build SNARKs for NP from LWE, or like there are many ways of phrasing this question. You could ask about how to do it from any polynomial time falsifiable assumption, unlike IO, would be very nice. Or if you're afraid, like there are some barriers that suggest this might be difficult. So if you're afraid of these barriers, then fine. Assume like sub-exponential LWE. Now there's definitely no concern there. Like so, anything in this space would be great. Any way of building SNARGs basically without having to solve the entire obfuscation problem would be wonderful. And something that like on the theory side that we really don't understand right now is building SNARGs with a short common reference string, which is like if you think about the problem from first principles, that's what you would probably want, not to have this giant reference string that's used by the prover and then some other reference string used by the verifier. But we know basically nothing about this. So it'd be great to understand this better. Sorry? Like polylog, like the proof length, like polylogarithmic. The constructions that we have succinct proofs but non-succinct reference string, which is not really desirable.
So non-succinct is polynomial indeedness line?
Yes. Yes.
To verify kind of randomly access parts of it, the same for the existing.
Yeah, there's no. It's you generate basically two reference strings, a short verifier reference string that's correlated with a long prover reference string.
Can you go back for 1 second for the previous one? Can you say something about the assumption in the last row?
Oh, this one? Yes. So we also have a result that doesn't use obfuscation. It uses the existence of a witness encryption scheme with a certain kind of propositional proof of correctness. So like you need so it's an assumption about the way that you prove the decryption correctness of a witness encryption scheme. So it turns out that if you have IO, then you can do this. So it's a weaker assumption than IO. And we have at least a heuristic construction of such a witness encryption scheme that doesn't use IO, but we don't have it from like reasonable assumptions.
So somehow your first slide was pictures of two proofs, right? Like the one with the triangles.
Yes, and magically like
So this is somehow related to
Yes.
this, right?
Yes.
But in general, do these two pictures relate to anything else you said? Like how does everything else you say relate to the normal notions of proofs that you showed on the first slide.
Yeah, it's not immediately clear because proof complexity, you normally think about the complexity of proving tautologies. It's like a co-NP type of thing, whereas we've been talking so far about proof systems for NP. And so, yeah, a priori, it's not clear how they should be related, but in some recent works over the last few years, it's turned out that we've been able to tie these things together. For example, we have interesting proof systems for NP intersect co-NP, and where this notion of proof complexity seems to come into play. And in this work, somehow, like, proof complexity is coming up in some very strange way about where what's relevant is proof complexity properties of the cryptographic building blocks that we're using in the protocol. It's like a very strange connection. Yael will maybe mention this a little bit in her talk. Yes.
What is the adaptive and adaptive sounders?
Yeah. So when you have a reference string, there's for a non-interactive proof system, there's this additional caveat / question of, well, do you allow the adversarial prover to pick the statement that they're working with dependent on this reference string? The proof system is called adaptively sound if it's sound against provers who can choose the statement adaptively. And in practice, this is something that you definitely want. This is actually an important property.
The WW doesn't contradict Gentry Wicks?
I'm sorry, I can't hear you.
The WW construction doesn't contradict Gentry Wicks?
No, so we haven't talked about Gentry-Wicks, but no, basically Gentry-Wicks just says that to build adaptive snarks with this adaptive security property, you need to make a computational assumption against adversaries that run in time, which is exponential in the statement length, which they do. So there's no problem. Yes.
On the next slide, you mentioned this open problem about, I assume that means without CRS?
No. It's still with a CRS. Without a CRS, it's known to be impossible.
Alex, the second question is also about for NP, right? Like
yes,
classes.
Yes, and Yael will also maybe talk about some of this. Great. So I'm going to wrap up now, but like a quick word on how non-interactive protocols, like how do we build them? Because we haven't talked about this at all. So there are two things that are good to know. One is that you can generically build non-interactive protocols using something called the Fiat-Shamir heuristic, which converts public coin interactive protocols into non-interactive ones. Yael is going to talk about a second approach for building snargs that is not based on Fiat-Shamir, using this notion called a non-signaling probabilistically checkable proof.
How close are we to solving this problem question on the previous slide?
What do you mean by how close? It's something that we've been working on. Something that we've been working on for a long time, and Yael will answer that question. Yeah.
Hopefully close. Otherwise, it's going to be sad.
Yeah. So, okay, just to.
Are they equally close or?
Oh no! The first one we expect to be much close. I expect us to be much closer on the first one than the second one. Handling short CRS seems to be very difficult to me, but the first one should be possible. All right. So, like, what's going on with Fiat-Shamir? Heuristically, if you have a hash function, you can just generically compress at least any constant round interactive protocol into a non-interactive one by having the prover use the hash function to generate all the verifier's random coins by applying the hash function to the partial transcript of the protocol so far. And heuristically, whenever the interactive protocol is sound, it seems that the resulting non-interactive protocol would be sound. If you could prove this in general, then we would be done. We would actually solve both of the open questions that we just discussed, because you could apply Fiat-Shamir to Killian's protocol and get a succinct non-interactive argument system for all of NP. That would be wonderful, but unfortunately, we have counterexamples to exactly this plan. So this does not seem to be within reach. We actually, even from this year, there's this work of Kovratovich, Rothblum, and Sukhanov, which shows that, like, basically exactly the kind of Fiat-Shamir heuristic that you would like to apply to something like Killian's protocol to build a snarg for practice is broken. If you like, depending on some very specific choices that you make about how to do the Fiat-Shamir, it can just be broken when heuristic would predict soundness. So this is, it is, that's what this recent, yeah, that's what the, so okay, actually a previous work is like talks about breaking Fiat-Shamir for Killian. What this most recent work is doing is Fiat-Shamir for a commit and open protocol that uses the this GKR protocol as a sub protocol. It's like,
Why is it open for Killian?
it's not clear at all, but there are these counterexample protocols. Like if you choose either a bad choice of PCP or a bad choice of collision resistant hash function for Killian's protocol, you can come up with attacks. You can show that for any choice of Fiat-Shamir hash function, that there's an attack on the soundness. It's quite non-obvious, but it's using these like diagonalization tricks.
It's not in the random arc. Is it in the random arc?
No. Yeah. So if you model the hash function as being a random oracle, then Fiat-Shamir is sound very, very generally, and everything is basically good.
What do you mean by very, very generally? Like
For any constant rounds public coin interactive argument that is even computationally sound, if you apply Fiat-Shamir to it, then it's sound in the random oracle model. This we know, and this is very important, and it underlies basically everything that Justin does in the afternoon. So, sorry, is it still unclear what's going on?
Sometimes it's not I guess it's not.
Maybe let's make questions.
I mean, even public client is not a general. But I know it doesn't matter. I know some examples.
Okay, I understand. Sorry for being too informal about it. But yeah, so basically the situation is that if you want to compile computationally sound arguments, it's really not clear how to do things without using random oracles, and that's a huge open problem that would be good to understand. If you focus on compiling interactive protocols that are sound against unbounded provers, if you assume statistical soundness from the beginning or something related to statistical soundness, then we have a ton of results over the last few years on how to instantiate the Fiat-Shamir heuristic with the standard model hash function or CRS model hash function. And the basic way you do this is using some notion of hash function security called correlation intractability. So unfortunately, I don't have time to talk about it, but just to give a, yeah, there's a lot to talk about, right? Yeah, right. But like just to summarize, some things that we know how to do based on this paradigm is building non-interactive zero-knowledge arguments, for example, from the learning with errors assumption and the DDH assumption. These are things that we didn't know how to do before that we now know how to do using these standard model Fiat-Shamir instantiations. And we know how to build succinct non-interactive arguments for batch NP languages, where the question here is like an amortization problem. You have k NP statements, and you would like a prover would like to prove that all k of these statements are true. If you had a snarg, you could just do it. Fine, it's just an and of k different statements. But in a batch, in a snarg for batch NP, you relax your succinctness requirement to allow the proof to grow with a single witness, but not the number of witnesses. It should be polylogarithmic in the number of statements that you care about. And so it turns out that this distinction is very important, and this is something that we know how to build, whereas snargs for NP are much harder. Especially like using Fiat-Shamir. Like using Fiat-Shamir, we know how to apply Fiat-Shamir to basically a batch version of Killian's protocol to get a snarg for batch NP, whereas like Fiat-Shamir for a single shot Killian is something that we really don't understand how to analyze at all. So yeah, those are and what Yael will talk about next is how to build snargs for P and other computations, assuming this snarg for batch NP as a building block. So it's a second approach to building non-interactive protocols that does not go through Fiat-Shamir. And yeah, so there are, okay, these questions won't make sense, but I'm happy to talk about them offline. But yeah, like understanding Fiat-Shamir for arguments is something that I think would be really great to do. And yeah, thanks for listening, and we'll see you in a little while for Yael's talk.
Are you going to post the full slides online?
What did he ask?
Perfect. So crazy.
I'm not sure it's right.